Okay, thank you very much for the invitation. So I want to talk about some recent work jointly with James Martin, who's at Oxford, on this model called the push ASEP. I presume most of you know what the ASEP is, so let me refresh your memory. So an ASEP, or asymmetric simple exclusion process, is a particle system where you have n1 particles on a ring of size L. So I take periodic boundary conditions, and it's partially asymmetric, and so I represent particles by 1 and holes by 0. So if a particle is followed by a vacancy, let's say clockwise, then it hops with rate 1, and if it's the other way around, it hops with some fixed rate t. And usually, without loss of generality, you can take t to be between 0 and 1. So this model is simple enough that the stationary distribution, or the steady state, does not depend on t. So all, in particular, it's uniform. So all states are equally likely, and so you have this very simple expression. So the natural generalization of this is the multi-species ASEP, where you have, let's say, different kinds of particles, some which are more muscular, let's say, and some which are less so. So you have, let's say, S kinds of particles, and we take the strength order where S is stronger than S minus 1 and so on. And zeros are again vacancies. So if you have a ring, and so you have a ring of L sites, and each site is occupied by exactly one of these particles, and of course, I think of vacancies also as particles. So then I can index my state space by this partition lambda, which has lots of S's, lots of S minus 1s, etc. Like so. And the total number of particles is L. And the transitions are, as you can imagine, similar to the single species case. So if you have a larger particle followed by a smaller particle, then they can exchange with rate 1, whereas if you have the other way around, they will exchange with rate t. Okay, so stronger particles tend to go clockwise, weaker particles tend to go counterclockwise, and something, so if you have something in between, then they do mixed motion. So there's this beautiful theorem by Ferrari and Martin, which gives an exact formula for the case of the multi-species TASEP, where t is 0, so where you have only the forward clockwise motion. And so what it says is that in that case, if you have the TASEP with content lambda, the stationary probability is, if you like, the partition function is this very simple product of binomial coefficients. So it's not at all obvious. And what it says is that, so the stationary probability is some integer divided by this product of binomial coefficients, and where capital Mi is the sum, is the tail of the Mi, so small mi plus up to small m. And so this integer that is there has a very nice combinatorial interpretation. So if nothing else, I would like you to take this away home. So what you do is you consider a discrete cylinder, okay, with height S minus 1 and length the size of the system. So for this partition, there are two particles of type 4, one of type 3, etc. In that case, you put the number, you pick a place particles randomly, two particles randomly on the first row. That 2 corresponds to the number of 4s. You place 3 on the second row, which is the number of 4s plus the number of 3s, and so on. So you get a configuration on a discrete cylinder of particles and holes. And now you do the following process. So I'm going to tell you how to go from this system, this configuration, to a multi-species TASEP. So there's a, okay, so since I see that I'm very short on time, I'll have to go through this fast. So there's a way of labeling particles in each row systematically so that you get a configuration downstairs. And in this case, it's this particular configuration. And the theorem says that all possible configurations that under this projection come to this, precisely this configuration will be that positive integer. So the number of configuration, the cylinder configurations that project it into that will be proportional to the stationary distribution. It's a really beautiful interpretation. And this has been generalized to the multi-species ASEP, where there is this T parameter again, and this by Martin. And in all of this, the rates are just 1 and T, and there's no inhomogeneity. And so there's, okay, so so let me not go into this. So the question is, can you generalize this model so that you have inhomogeneous rates? So it turns out that the correct thing to do, so if you just make the rates of the ASEP depend on sites, let's say if a particle at site I and a vacancy at the next site you say has rate alpha I or something, then that is not the right thing to do. Somehow that just blows up in your face. So the correct thing to do is to consider the push TASEP. So what is the push TASEP? Again, it's like the TASEP, except that there's this pushing going on. So what does that mean? So again, you have a ring of size L, let's say single species, and just you have N1 particles. Then the dynamics is as follows. So whenever the particle at site I wants to jump, it will not jump to the next site, but it will jump to the next available site. So it will keep looking past all the ones that are available. The first vacancy that it finds, it goes and sits over there. That's the dynamics. Another way of thinking about it is that this one pushes the one next to it, which pushes the one next to it, and so on until it rests up to there. So that's the motivation for the name. And here I can say that the rate of this jump depends on the site. So that's, I've given it rate 1 by beta I. And in that case, it's fairly straightforward to show that the steady state is proportional to the product of the beta i's, where you take the product over all locations, and the partition function is the elementary symmetric function. And now if you can do a multi-species version of this, where again you have so many particles, let me just show you with an example. So let's look at this configuration over here. So when this particle jumps with rate 1 by beta 5, because it's at the fifth site, it will go and find the first available smaller particle, which is a 1, which will go, because this is on a ring, it will go clockwise and keep finding the first available smaller particle, which in this case is a 0, and then it will go and all these 3 will cycle. Okay, so this is the dynamics. In this case, we are able to get exactly multivariate generalization of the stationary distribution or the steady state of the ASEP, which is given in terms of this ASEP polynomial, which I did not have a chance to explain. And the partition function is this very important symmetric polynomial called the Macdonald polynomial. It's very important in representation theory. In particular, if I set all my push TASEP rates to be equal, I get exactly the same stationary distribution as the TASEP. And to end, let me show you one non-equilibrium theorem. So all of this I said so far is for the steady state. Now, suppose you start the push TASEP, multi-species push TASEP, in a configuration where the last, let's say, k plus 1 through L sites are in decreasing order. Then, if you run the system for any time that you like, and you look at any observable that you like whatsoever, which depends only on the first k sites, which is disjoint from this, then the probability of any such observable is invariant under any permutation of the last k plus 1 through L rates, L minus k rates. So this involves the coupling of Poisson processes, and it's truly a non-equilibrium result. It holds for all finite time for any observable that you like that depends only on the first case. Okay, so with that, I will stop and thank you for your attention.
One quick question.
Which correlation function? Right, so for the non-equilibrium, yeah, so for the pushed SF, we have explicit formulas for the nearest neighbor correlation, 2-point correlation, and for the current. So what happens is that there is a projection. So you can go from larger species to smaller species by coloring argument. And so that kind of calculation is essentially reduces to a two species calculation, which we can. Yeah. Thanks.
Okay, let us thank the speaker again.